Hi all. Today we are here for the seventh problem solving session for the course Spectroscopic Methods, Spectroscopic Techniques for Pharmaceutical and Biopharmaceutical Industries. I hope all of you can hear me. If you're not able to hear me, please post a message in the chat box. Okay. Yeah, this week we have been introduced to the UV spectroscopy and its applications, and we have gone over through how electronic spectroscopy of a conjugated system, and what are the applications of different spectroscopic methods, and different applications of electronic spectroscopy. And yeah, so today I'll be going over a couple of problems about how the electronic spectroscopy of a conjugated system is done, and I'll also be going to discuss a couple of problems related to Beer-Lambert law. Yeah, please let me know if you're not able to hear me. Are you able to hear me? Can you just post a message in the chat box? That'll be great. Yeah, thank you. Yeah, so let me start with the first problem for today. So it's about the absorbance and transmittance. So in the lecture we have been introduced to what is transmittance and what is absorbance. So yeah, sorry, yeah. So absorbance where T is transmittance. So it sorts of absorbance sorts of gives us a information about how much incident radiation has been absorbed by the sample. And here we have been given a solution of 7.25 into 10 to the power 5 molar solution of a potassium permanganate, and it has a transmittance of 44.1%. So and it has been measured at a 2.1 centimeter cell, and it has been measured at 525 nanometer, and we have been asked to calculate the absorbance of this particular solution. So yeah, so where do we in general measure the absorbance for estimating the concentration? So if you have an absorption spectrum of any chromophore, where the x-axis being the lambda, the um, the wavelength, and y-axis being the absorbance. And if you in general for a chromophore, if the absorption spectrum looks like this, we in general measure the concentration at the absorption maximum, which is like lambda max. So has covered in the class Y. It has been 1 second. Yeah, so has covered in the class Y. It has been measured around the why the concentration estimation is done using the lambda value at its where the absorption is maximum. So yeah, we in general use the lambda max for estimation of concentration. That's because the error in absorption is going to be sort of lesser if we change the lambda slightly little bit. But if you are in somewhere in this range, okay, let me highlight it. Yeah, if you are in somewhere in this range, the error in absorbance value, if you are slightly off in terms of your lambda value, is going to be higher. So that's why you always measure the concentration and always do the concentration estimation when the lambda value is lambda max. And yeah, So the first question is to find the absorbance of the solution given the transmittance. So a question absorbance is what we have to find. A is equal to minus log of T, where T here is 44.1%. So T is going to 44.1% is equal to 0.441. So this is minus log of 0.441. So if you do the calculation, it will, this is going to be minus of minus 0.356. This is equal to 0.356. So the absorbance of this particular solution is 0.356. And the second part of the question is to find the molar absorptivity of KMnO4. KMnO4 is potassium permanganate. So we have been asked to find the molar absorptivity, which is epsilon. So how to find epsilon? So we know that from Beer-Lambert law, which has been covered in the class, we know that absorbance of any solution is equal to epsilon Lc, where epsilon is the molar absorptivity, and it is a property of a particular molecule. It's the property of a molecule. L is the path length of the light, and L is the C is the concentration of the chromophore. This equation has been covered in the class. If you have any particular doubt about how it is being derived, you can always go back and check the class. If you find any difficulty in following the steps that has been explained in the class to derive this particular equation, you can always come and ask us back. So yeah, so we have to find what is the epsilon. So epsilon, epsilon is going to be A by Lc, where A is the absorbance, which we have found out. So this is going to be the A, and we have to find what is the L. L is going to be the path length, which is determined by the length of the cell. So it is 2.10 centimeter. C is the concentration. So concentration is here. So A is 0.356 divided by 7.25 into 10 to the power 5 molar into, we have 2.10 centimeter. So this is going to be this is going to be 2.34 into 10 to the power 3 mole inverse centimeter inverse. So 1 molar solution is 1 molar solution is equal to moles per liter inverse, right? So this is going to be 2.34 into 10 to the power 3 mole inverse liter centimeter inverse. So this is how the molar absorptivity has been calculated given the absorbance value, and the concentration and the length of the cell, or which corresponds to the path length of the light. Yeah, the second question in this part is to find the it's about a complex a solution containing the complex of bismuth and thiourea, and it has a molar absorptivity constant to be 9.32. Yeah, molar absorptivity coefficient to be 9.32 into 10 to the power 3 liter centimeter inverse mole inverse, and it has been calculated at a and the molar absorptivity at this particular wavelength, which is at 470 nanometer, and the concentration is being given, and the path length is also being given, and we have been asked to find what is the absorbance value. So we know that is absorbance is equal to epsilon LC. This is from Beer-Lambert law. And epsilon is molar absorptivity coefficient, which is 9.32 into 10 to the power 3 liter centimeter inverse mole inverse, and length L path length of the light is 1 centimeter, so 1 centimeter into 5.67 into 10 to the power minus 5 molar, and all these units cancels out, and we have seen in the lecture that absorbance is a unitless quantity, and this will become, upon doing the calculation, this is going to become 0.528. Okay. The next part is to find the percentage transmittance of the solution described in the part A. So we had seen the similar calculation in the previous question, where absorbance is equal to minus log T. So transmittance is equal to 10 raised to minus A, because log is not natural logarithm, it is log 2 base 10. So transmittance is going to be equal to is equal to 10 to the power A. So A is 0.528, right? We have found it in the first question. Sorry. We have found that in the first question. So this is going to be 10 to the power minus 0.528. If you have any doubts, how did we come to this equation, can you please comment on the chat box? I hope everyone understood how we come from this equation to this one. If you're not able to, please comment on the chat box. Okay. So A is going, transmittance is equal to 10 to the power 10 raised to minus 0.528. This is equal to, if you do 10 to the power minus 0.528, it comes to 0.296. And we have been asked to percentage transmittance, right? So percentage transmittance is equal to transmittance into 1000. So this is equal to 29.6%. Okay. Now the third question is to find the molar concentration of a complex in a solution, that is the absorbance described in 1, when measured at a 470 nanometer in a 2.50 centimeter cell. So absorbance A is equal to epsilon LC. So let me just tell you about what all affects the absorbance. So epsilon, if molar absorptivity is defined at a particular wavelength, and it is characteristic for a chromophore, and characteristic of a chromophore. So if you have a solution of a particular chromophore, it is going to be the absorbance is not going to change if the concentration and the provided the concentration and the path length is the same. So the other two parameters that can affect the absorbance value is the path length or the concentration if you have given a particular chromophore, and if you are measuring the absorbance at the same lambda value, at a particular lambda value. So we have been so if the absorbance value is 0.528 as we described in part 1, which is 0.528, and we are saying that epsilon is same because we are measuring for the same we are going to measure it for the same substrate, which is bismuth area complex. So it is going to be 9.35 into 10 to the power it's 9.32 into 10 to the power 3 liter centimeter inverse mole inverse. And path length, in the first question it was 1 centimeter. So in the third part it is 2.5 centimeter. Okay, so if your A is going to be if your A is going to be constant and epsilon is also constant because you are using the same substrate, and if your L has increased, then your concentration should decrease in order to maintain the equality in the equation. So what we are sort of predicting is the concentration is going to be lower compared to however it was in the part 1. So let's calculate what is the concentration. C is equal to A by epsilon L. So A is 0.528 divided by 9.32 into 10 to the power 3 liter centimeter inverse mole inverse. L is going to be 2.50 centimeter. So 0.528 divided by 9.23 into 10 to the power 3 into 2.5, it's going to be 2.28 into 10 to the power minus 5, and centimeter inverse and centimeter inverse cancels out, it will become liter inverse mole. So this is 2.28 into 10 to the power minus 5 molar. So we had seen that in the first part the concentration was 5.67 into 10 to the power minus 5. Now the concentration has reduced in order to maintain the equality of this particular equation. So as we increase the path length, the concentration has reduced because the absorbance is the same. So in general, in a typical scenario, we have to find what is the concentration of a particular sample given its molecular absorptivity and absorptivity at its lambda max, and we'll be given a particular cell to measure the solution, using which you can estimate the concentration of a sample. So in general, we uses this Beer-Lambert law to measure the concentration of a of a solution, and we in general know what is its molar absorptivity. Yeah. So before it, I'll come to it in a bit. So yeah. So so we can treat the conjugated systems as conjugated systems as particle in a 1D box sort of model, where as the delocalization increases because of extended conjugation, it results in an increase in lambda max. So this is something which we can see by solving this problem. So if you have a particular mass of if you have a particular mass which is moving in a which is being localized in a certain length, we can approximate it to a free particle in a 1D box, and the energy of the particle inside the box is given by n square h square by 8 ml square, and this part has been covered extensively in the lecture. If you have any particular doubt in understanding what is it, how is it being derived, please let me know. We can discuss about it now. The other thing is the wave function associated with this particular particle is given as psi n of x is equal to root of 2 by L sin n by x by L, and where n is the quantum number associated with the wave function, and it can vary between 1 to infinity. Yeah. So this has been solved by we arrived at this particular wave function, and we have solved the energy of the particle by using the Schrodinger equation. So the first question here is to consider the excitation of an electron from the first to the second energy level uh, for a particular molecule like ethylene, and what is the wavelength of the light required to affect this transition, and we assume that the length of this particular box to be 1.33 angstrom. So let me just explain you. So ethylene is going to have CC single bond, and we are looking at the electron being localized as a cloud between this carbon bond, and the probability of finding the particle in any of this x direction is being given by this can be defined by using this particular wave function. So we have to find okay. So this is something with n is equal to 1, n is equal to 2, and we have to find what is the energy associated with this transition, and where this delta E corresponds to hc by lambda, and we have to find what is the lambda associated with it. Okay, so from this particular equation we can calculate what is energy associated with n is equal to 1, which is the ground state or the first energy level, and by putting n is equal to 2 we can calculate the energy in the second energy level. So E1 is equal to 1 square h square by 8 ml square, and E2, the energy at the second energy level, is going to be 4 h square by 8 ml square, and delta E is equal to 4h square by 8 ml square minus h square by 8 ml square. So this is equal to delta E is E2 minus E1. So this is equal to 3h square by 8 ml square. So H is going to be Planck's constant, that is 6.626 into 10 to the power minus 34 joule second. M is mass of electron, which is 9.1 into 10 to the power minus 31 kilogram. L is the length of the box. So length of the box is given by the CC double bond length, which is 1.33 angstrom. So this is 1.33. 1 angstrom is 10 to the power minus 10 meters. So it is 1.33 into 10 to the power minus 10. Okay, let's do the calculation. Okay, one other thing is, let's come to delta E122 is equal to H nu 12. This can be equal to Hc by lambda 12, and we can equate it with this particular equation. So Hc by lambda 12 is equal to 3h square by 8 ml square. H can be cancelled and we have to find what is lambda 12. That is 8 ml square C divided by 3h. So it is 8 into 9.1 into 10 to the power minus 31 into L square is 1.33 the whole square into 10 to the power minus 9, right? Whole square into C is 3 into 10 to the power 8. So this is meter square, meter second inverse. This is in kilogram. 3 into 6.626 into 10 to the power minus 34. So H has a unit of joule second and this is equal to kilogram meter square second square inverse. So this is kilogram meter square second square inverse. Let's do the calculation. So 8 into 9.1 into 1.33 into 3 divided by, basically these two 3 we can just brush it off. This is coming to be 14.61 into, okay, so meter. So if you cut off everything, it will come back to this is meter second inverse, okay, meters by second inverse. So these will cut off. Yeah. So this will makes the unit to be meter. So this is going to be 14.61 nanometer. So the wavelength which is associated with the transition of first energy level to the second energy level, first energy level to the second energy level of carbon-carbon bond, carbon-carbon pi bond of ethylene is given by 14.61 nanometer. Yeah. Now if you the second, yeah. Now we have been it's the part of this that particular problem. Now we have to extend the localization to from ethylene to 1,3-butadiene. So ethylene was a CC double bond. 1,3-butadiene is this particular molecule. Okay. Now we have been asked to find what is the energy, what is the wavelength associated with the transition where, sorry, this is equal to 1, 2, 3. Now we have been asked what is the energy gap between 4,1,3-butadiene. Okay, does this, and we have to find whether it is corresponding to a bathochromic shift or a hypsochromic shift. So now the particle is no longer confined to a 1.33 angstrom box, whereas it has been confined to a 4 angstrom box. Okay, so that corresponds to the total length of this extended length of this conjugated molecule. So we have to find what is the wavelength required to affect this affect the same transition, which is 1 to 2. So we had seen in the previously derived formula, lambda 1 2 is equal to 8 ml square C by 3H. 8 ml square 8 ml square L square C by 3H. And if we are not changing anything else, we are just changing the L value. C is a constant, which is the speed of the light. H is Planck's constant. M is the mass of electron. And all these things are going to be constant, and 8 and 3 is also other numerical constants. So lambda 1 2 is directly proportional to L square. So if you have lambda 1 2 of A by lambda, okay, ethylene diene, okay, not ethylene diene, sorry, one 3-butadiene this is equal to L square of 1 3 or L of 1 3-butadiene, L square of 1 3-butadiene by L square of ethylene. So we can make it as lambda 1 2 of 1 3-buta LF13 diene by L of ethylene the whole square. So we know that LF13-butadiene is 4 angstrom, whereas it's 1.33 angstrom for ethylene. So 4 divided by 1.33 the whole square. This is going to be 4 divided by 1.33. 9.043. Now we have to find what is lambda 12 of 1,3-butadiene, and it's going to be 9.043 into lambda 12 of ethylene. So this is 9.043 and the lambda for ethylene was 14.61. So that's going to be 14.61 into 9.043, 132.118, and this is at particular nanometer, 14.61 nanometer, so this is going to be 132.118 nanometer. Yeah, so we had seen that as we increase the conjugation, this one was corresponding to 14.61 nanometer and this one was corresponding to 132.11 nanometer. So as you increase the conjugation, you increase the lambda value. So since the lambda increases when L increases, so we are sort of seeing a bathochromic shift upon delocalization. So okay, now let's come to a bit more complicated problem. This is when you just look at it, it seems to be a bit complicated problem, but when you read the problem a little better, it is just asking you to find what is the it is just asking you to find what is the energy gap between n is equal to 6 and n is equal to 7 for a particular system, and we have to find what is the L. L depends upon how many number of atoms are conjugated. So here we have 11 carbon atoms and one second. Sorry. So here we have 11 carbon atoms and 1 oxygen atom where it is conjugating. So consider we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you have conjugating systems. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have 11. Okay, let me number it. So you have 11 carbon atoms and 1 oxygen atom. and you have, yeah, and you have like and you have 2, 4, 6, 8, 9, 10. 10 electrons being um, 10 electrons being conjugated along these along this distance L, and we have to find what is the L. And in systems where you have like conjugated double bonds, the okay, not that this double length bond length is different from uh, this particular bond length. Both the bonds are going to have same bond length of 1.4 angstroms. Okay, now we have to find what is, so you have like a you have to find what is the length L if one of the bond length is 1.40 angstrom, 1.4 angstrom. So let's find what is the L, and once you find the L, you know what is, how to find how En is being calculated, and we have to find it, do it for n is equal to 6 and n is equal to 7. So yeah, in the ground state of retinal, which has around 11 carbon atoms and 1 oxygen atom, each level up to n is equal to 6 is occupied by 2 electrons. So n is equal to 6 is the highest occupied molecular orbital, and we have to calculate, and the average interatomic distance is 140 picometer, which is equal to 140 picometer is equal to 1.4 angstrom, and we have to calculate the separation of energy between the ground state and the first excited state. So the ground state here is going to be n is equal to 6, where until which um, uh, you have the electronic states being occupied with 2 electrons, and you have to find the separation in energy. You have to find what is delta E between E is equal to 6, E with n is equal to 6 and E with n is equal to 7. And we have to find what is the frequency of radiation required to produce this transition between these two states. Basically, delta E is equal to h nu. And you have to find what is the nu that is being asked in the second part. And the third part is just what if when you increase the conjugation. That I think we already have seen in the last part of the question, last question. But it's okay. Let's go over it in a systematic manner. Now we know what is the average bond length, which is equal to 1.40 angstrom. From that we have to, so we have like 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11. 11 such bonds. So we have to find what is the L value for it. So if you just have something like this, let's find how much this one will, if this is 1.40 angstrom, let's find how much this one will be. Okay, so okay, one second. Yeah. So if you consider two bonds which are this sort of makes a isosceles triangle where both the angles being both the sides being same, and if you split it with 2, you have like, yeah, yeah. mm, 1 second. This bond length is going to be 120 degree. This carbon-carbon bond length is going to be 120 degree. So when you split it to half, it is going to be 60, and this is a 90 degree angle, and this is 30 degrees. So basically you are left with 30 degree, 60 degree, and you have 1.4 angstrom, and you have to find what is this length. Okay, and this bond length is going to be yeah, this is opposite to 60, right? So it is, let it be a small l. Small l is equal to sine 60 into 1.4. So basically sine 60 is going to be L by 1.4. So you need a little bit of geometric understanding to find this. Once you know the value, I think you can just by heart it and use it for any conjugated carbon-carbon conjugated systems. So it is going to be sine 60 is going to be sorry. One second. Yeah. Point 866 into 1.4, sine 60 is 0.866 into, yeah, it's going to be 1.21 angstrom. So, or 1.20 angstrom. You can just approximate it as 1.20 angstrom and can be used for any conjugated carbon-carbon single bond system. So, yeah, the first question is to find what is the separation of energy between separation in energy between the ground state and the first excited state. So here we have to find what is the ground state. Here is n is equal to 6. So E6 is equal to n square 6 square h square by 8 ml square, and we know L, okay, sorry, we haven't found what is L. L is equal to 1.2 into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 such bonds, right? So into 11. So this is going to be 11 into 1.2. This is 13.2 angstrom. So anytime if we have to calculate what is the length of the box, you have to multiply 1.2 into number of bonds, or you can multiply 1.2 into 2n minus 1, where n is number of double bonds. So here number of double bonds is 1, 2, 3, 4, 5, 6. So n there are 6 double bonds. 2 into n is 2 into 6 minus 1, which is going to be 11. So it's the same as what I have done here. So L is equal to 13.2 angstrom, and M is mass of electron. So this is going to be 9.1 into 10 to the power minus 31 kilograms. So this is equal to, yeah, let's keep it this way, and we have to find what is the first excited state. So first excited state is with n is equal to 7. So E7 is equal to 7 square h square by 8 ml square, and you can find what is delta E is E7 minus E6. That's going to be 7 square h square by 8 ml square minus 6 square h square by 8 ml square. So this is going to be 7 square minus 6 square by 8 h square by 8 ml square. So this is 49 minus 36 divided by 8. H is 6.626 into 10 to the power minus 34 divided by 9.1 into 10 to the power minus 31. L is this is in joule second. This is in kilograms, and L square is in, yeah, L square is in 13.2 into 10 to the power minus 10, which is 1 angstrom is 10 to the power minus 10 meter. So this is in meter. So this is going to be 1 second. Yeah. So 6.626 divided by 9.1 into L square. So it's 1.3, it's a 13.2 square and yeah, this is going to be 0.00417 into, okay, we'll do the 10 to the power. So 49 minus 36. Yeah. Into 30. So we can write it as 6.77 into 10 to the power 14, and this is joule seconds, and you have a denominator with kilograms. Okay. Oh, sorry, I made a mistake in the calculation. One second. This is supposed to be square. Okay. So 49 minus 36 is 13 by 8. 6.626 square is This is 43.9 into 10 to the power minus 68 divided by 9.1 into 10 to the power minus 31 into 13.2 square is 174.24 into 10 to the power minus 20, and this will come to 0.0449 into 10 to the power 20 minus 68 plus 31, so 10 to the power minus 17, and this will come to 44.9 into 10 to the power minus 40, and this should be in joules, right? And the second part of the question is to find the frequency between the radiation, and we know that delta E is equal to h nu, and we have to find what is nu, so we can just divide delta E by h. When you do that, we will get the value in second inverse, which is in hertz. I'm not doing that particular calculation. You can take it forward because we are already up with the time, with the scheduled time. Yeah, that's all I have to tell you today. Yeah, the second part has been covered in the previous part, where when L increases, when the delocalization increases, L increases, which in turn increases the lambda, which corresponds to a bathochromic shift. Yeah, that's all. Yeah, if you people are patient enough, we can just do the we can just find the frequency. Otherwise, I would like to end the session for today. Do you have any particular question from today's lecture, today's problem solving session? So the first part of the problem solving session, we have gone over the Beer-Lambert law, and we first found what is the absorbance from a given particular transmittance, and we came to Beer-Lambert law to find the molar absorptivity of KMnO4 given the concentration and the path length and the absorbance value, which has been calculated in part A. Second question, we have been the similar formulas we have been using to find the absorbance and the percentage transmittance, things like that, and we have found how the absorbance being affected by epsilon or affected by L and C, path length and the concentration. Second part, we have just gone over a problem where the ethylene with ethylene, how the what is the wavelength of the light associated with the transition from n is equal to 1 to n is equal to 2 in ethylene. The second question, we have looked at the path length has been increased for 1,3-butadiene, and how is it being affecting the wavelength of the excitation for the same between the same levels, and will it cause a bathochromic shift or a hypsochromic shift. And now we came to a comparatively complex delocalized system, and we have seen how we find the length of the box given the number of double bonds and all, and yeah, from which we have calculated how the what is the ground state and what is the excited state given the number of double bonds. And yeah, the second part of the problem, which I am not finishing here today in the lecture, is to find what is the frequency of the light associated with this transition, and for that you just need to divide the obtained E value, the energy of transition, by the Planck's constant. If you have any particular question from whatever we have discussed today, can you please comment it on the chat box? I will be happy to discuss. Yeah, thank you very much for joining. If you don't have any particular doubts from today's problem solving session, I would like to end today's session. Thank you all for joining.